Hello, everyone. My name is Cayman Nava. I'll be talking about navigating Eth2 with simple Serialize. So just before we get into everything, I just want to introduce myself. I'm a technical lead on the Lodestar project. This is a project by ChainSafe. We're writing an Eth2 client, and we're writing it in TypeScript. If you see those two pictures of me, those are my avatars. So maybe we've interacted online. So this is kind of the overview we're going to go over. It's going to be kind of fast. I have a lot of slides, and I really want to get through it all. But first, before we get into the details of this simple serialize, we're going to say figure out why it even exists in the first place. And then we're going to dig into how it's used in Eth2, kind of go over the different aspects of it. We're going to look at it in practice, so different implementation techniques, and then finally get into some benchmarks. And then if there's any time, then we'll go into questions. So why SSE? In Ethereum 2, in Ethereum in general, we have a lot of data that we're trying to Merkleize. And the reason that we Merkleize this data is so that we can make proofs, succinct proofs about it. In Eth2, we have an even more of a need for these proofs to be small than in Eth1. So we have stateless clients by default. We're going to have a lot light clients kind of as a first-class citizen. So some of the techniques we used in Eth1 don't quite work in Eth2. Another thing, the Eth2 state is very different than the Eth1 state. So we have a lot of data structures in Eth2 that we're kind of getting consensus on. We have this entire machinery that's handling the proof-of-stake system. And all of that is going to be Merkleized in Eth2. We'll look at some of that. So some differences, some things that are different between Eth2 and Eth1 with respect to how we're Merkleizing data. So one big thing is in Eth1, we're using hexarray tries. Eth2, we're using binary trees. The reason is the proofs are significantly smaller. Another thing to note if you're coming from the Eth1 world, all of this data that we're Merkleizing, we're not dealing with sparse trees. These are full-ish Merkle trees. And the data that we're dealing with is much more richly typed, and it's much more heterogeneous than just the 3 or 4 different things that we're Merkleizing in Eth1. So here's kind of just it's a big list. I'm not really going to go into it, but the idea here is that there's a lot of different structures. This is just the beacon state in Eth2. There's a lot of different substructures, different things that we're Merkleizing, and so we need a consistent way to be thinking about this landscape. And so in Eth2, this consistent standard for Merkleizing data is SSZ. So about SSZ, you can kind of think of it as the type system for Eth2, at least in the consensus layer. We have these different types that we get. We have an unsigned integer, a Boolean, vector, a list, container, and a root. We'll go into a little bit of detail on all of these. But really important thing to kind of keep in mind as we're going through this, and I'll be highlighting it with some diagrams, these SSZ, these objects, these values, they all have an unambiguous Merkleized representation. And so you can think about all of these types, or all of these values, as if they were trees. And so going back and forth between the tree representation and kind of the data type representation will be very valuable from an implementation perspective when we get into that later. So real quickly, unsigned integer, we have ints from uint8 all the way to uint256. These are just kind of unsigned integers as you know them. In Eth2, we have validator balances, we have timestamps, we have block numbers or slots, and those are all represented as unsigned integers. So if we were to kind of represent this as a tree, this would be a tree with one node. It's a very uninteresting kind of tree. And we could kind of serialize that data. Each node in the tree is 32 bytes. So kind of the red section is where the actual data is, and the rest is padded with zeros. Boolean, it's a Boolean as you know it, true or false. In Eth2, we use Booleans mostly for bit lists. And so we can tell like if someone in a committee did something or didn't do something, if they signed or they didn't sign. And again, if you think about this as like a Merkle tree, it's just a single node, and most of it's padded zeros, but you use 1 byte. So here's where things start to get a little more interesting. The vector type that we define is a homogeneous collection. So there's just one type for all the elements, and it's fixed length. So the length is part of the data's type. So some examples in Eth2, validator public keys, signatures. So any kind of, or most of the byte arrays that we deal with are fixed length. Those are most of the vectors that we deal with. So the way that we represent this is in a tree. We basically just put all of the elements as leaves in the tree. And if the length of the tree is not a power of 2, then we pad it with 0 chunks. And if the underlying element, if more than one of the underlying element can fit into a single 32-byte chunk, then we compress as many of those things into that one chunk as we can. So let's say we have a vector of bytes, unsigned int 8. We can put as many of those, we can pack as many as we can into one chunk so that we're not just wasting a bunch of space in each chunk. The really notable time that we're doing this in Eth2 is for vectors of Booleans or lists of Booleans. So like committee bit lists, we tightly pack the Booleans as single bits. So we can get 256 Booleans in a single chunk. Oh, and if the element is actually bigger than 32 bytes, then first we Merkleize that element, and then we put the root into each leaf. So here's an example where we have a public key. A public key in Eth2 is a 42-byte length 42 byte array. So the way that we would represent this in a Merkle tree is, so 48 can be fit into two 32-byte chunks. The first chunk would be fully filled, and then the second chunk is like half filled, and then the rest is padded. We can imagine if we had an even longer vector, then we would just keep on adding chunks and then Merkleize as needed. In this case, this is just a tree of like depth 1, because there's only 2 elements. A list is our way of doing variable length collections. So they're like vectors in that they're homogeneous collections, so all the elements have the same type, but they're variable length. And the one gotcha that we have is that there's a fixed maximum length for these for these types. So this limit is part of the data type. And so in Eth2, some examples of this is different transaction types in the beacon blocks. Those are all lists. Committees of validators, because the committee size can grow and shrink depending on the total validator set. That's also a list, and the validator registry itself is also a list. Again, like in a vector, we put all of the elements as set all the elements as leaves when we're Merkleizing. But the difference here is that we add one additional level at the top. And the reason that we do this is so that we can have an extra node to say what the actual length is. So you may be thinking, so like what? It's like, how do you know what the actual depth of this tree is? Or how do you know how many elements there are? Well, this is the reason that we have a max length. And that reason is that we can have a fixed depth of our tree. Moving on. Let's see, containers. We have a container so that we can have so that we can have a way of putting together a bunch of types or a bunch of elements together that have different types. So it's heterogeneous. Every element has its own type. You can kind of think of this as like a key value store where we have the keys and the values kind of predetermined in their types. In Eth2, so we have like validator records where we keep track of the different data we need for each validator. Blocks, state. Most data structures in Eth2 are these containers. So again, it's all very similar to vectors. Every element is a leaf in the tree. So here's an example of a checkpoint, which is a data type in Eth2. This is a pretty simple tree. There's two different elements, epoch and a root. Both of those, each one would be a leaf. The first one, since it's a uint64, we're only going to be using a fourth of this leaf here. The rest is padded, and then the bytes 32 is using the entire chunk or the entire leaf. So where things get more interesting, kind of thinking about things from a Merkleized perspective, is when you have containers where some of the values in the container are containers themselves, or are bigger trees themselves. So this is kind of the structure you get in Eth2, where when you have when you get to these bigger structures. So like the beacon state is like a tree of trees of trees of trees, with many smaller subtrees below it. And a root, I'm calling this a separate type. It's actually just a byte 32 type with some special semantics around it. We treat this as a byte 32, but it has the special kind of ability that we can also imagine that the root is the root of another tree. And for that, we need to know the type of that subtree. So like for our example of a checkpoint earlier, the root subelement is actually the root of a beacon block. And it's not just a byte 32. So if we were to like imagine this tree of this checkpoint, again, actually the root, you can think of the root as containing the whole beacon block. And why this is cool, so like from like one checkpoint, you can kind of imagine expanding the data to an entire beacon block. Within a beacon block, beacon blocks have roots. You can expand that data maybe to a beacon state and like somehow navigate all the way to a shard state. And when you're thinking about like what this would look like practically speaking, you could be building like a Merkle proof that could be taking you all the way from like this checkpoint, and it could provide you one witness that takes you all the way down. So you could, within like one request, request either some historical state or some shard state that's like, that you would think would maybe be far away. So like in practice, let's kind of see how it's used. These are kind of the common operations that you do on it. So there's things that you would expect from like standard data types, just like getting and setting elements, iterating over things, seeing if something is equal to something else or greater than or less than. These are all kind of standard. And then you have your like blockchain specific things that you can do with it. And so that's serialization, Merkleization, and then like dealing with all of like the Merkle proofs. So you've actually got like 3 different ways of like looking at looking at data, and you can actually you can have at least 3 different implementations of that data. So like there's the structural way, which is where you imagine like a collection as maybe like a Python dict or a JavaScript object. There's the tree representation where you can imagine you could actually maybe work off of a tree directly. And then there's a serialized representation where you can deal with just a byte array. But all 3 of those things kind of could be potentially dealing with the same object abstractly, or the same. You could be thinking of them as the same object. There's definitely different trade-offs to storing the data in these different ways, and it's really interesting to look at these ways, looking at these 3 different ways because they have different trade-offs in practice. And so when we get to the benchmarks, we'll very briefly like look at like what the benefits are of using a tree, what the benefits are of using like the structural approach. And oftentimes like you kind of have to use a hybrid. So like we're building this Eth2 client and we're kind of using a combination of all 3 in different cases where it makes sense. So there's like structural approach. You can represent these objects as like native data types in whatever language you're working in. And it's great because languages are usually designed to like get out of the way. And so when you access different pieces of data, it's fast. It's convenient because it's built into whatever language you're using. The cons are that like when you actually go to Merkleize this data, you have to serialize the data, and then you have to like do a lot of hashing. So in our experience, before we were like even kind of thought about anything more advanced, we had this naive implementation where we would like Merkleize an entire beacon state. Just an empty beacon state would take us 15 seconds just to hash it, and we were dealing with 12-second block times. It just doesn't work. So like the cons are big when you're wanting to Merkleize data a lot. Kind of on the other side, very different trade-offs. Kind of on the other side of the trade-offs, actually, you have the tree implementation, and there's probably several different ways of implementing a Merkle. There's many different ways of implementing a Merkle tree or Merkleized data. The approach that we went with is capturing the tree as a persistent data structure, and so storing each of the nodes and the hashes of the nodes as a linked data structure, rather than storing them in an array or something like that. We have separate nodes with pointers to each of the children, and whenever we do an update to a leaf, we can kind of cache all of the pieces of the tree that don't change. So whenever large parts of the tree don't change, we can reuse that subtree. We can reuse the subtree, reuse all of that memory. And so this is really great for hashing because once you've hashed something, you already have the hash there. You just kind of like look at the node, you look at the position in the tree that you want to get that root. It's very fast to like clone a data structure because since we're kind of dealing with things immutably, all you have to do is like make a new pointer to the root of the tree. And it's really great for sharing data. Like in Eth2, for instance, we can store our beacon state as a Merkle tree, and when only a small amount of the validators change, or when only a small amount of the validators change or only a small piece of the state changes, we can reuse like a vast amount of the tree, and we can store many states where it's reusing maybe 50, 80% of the actual underlying memory. The cons, so when you're dealing with a tree, it's no longer just the same as dealing with like a language's native types, and so it's much less convenient if you're doing this naively. The data retrieval requires actually navigating the tree. So as we saw in the previous slides, the data is all stored in the roots, and you usually would have a kind of a pointer at the root of the tree. So you have to navigate down all the way. And then if you want to actually like get this unsigned int or get this Boolean, you have to deserialize the data at that point. And then very briefly, serialized, dealing with serialized data. You can imagine this as like just dealing with just just a byte array that has all of the data in it. This is great because all the data that we get over the network is serialized in byte arrays. And so maybe you only want to check one small piece of a very large data structure that's serialized. You wouldn't need to like first deserialize it, turn it into a tree or whatever. You would just only deserialize just the tiny piece of that you're needing to check. And it's really compact. You don't need this whole linked data structure that takes up a lot of memory, a lot more memory. The cons are that you have to navigate this byte array. Again, it's not as convenient. And then you have to deserialize any primitives that you're dealing with. So I've got one slide on benchmarks. It's really like benchmarks. It's not really benchmarks. It's relative. And so really, I just wanted to like highlight some like three big categories, or two categories, and some practical results. So we can look at iteration, and this is something that like really favors a native data type, a native piece of data. So iterating through an array, like a language's native array, is going to be very, very, very fast. Whereas iterating through a tree is going to be significantly slower because we need to navigate down from the root of a tree all the way to the leaves, and depending on how you do it, either start at the root again and then navigate down, or kind of pop your way along the tree. And so what we found by looking at benchmarks is that structural data is like 2,000 times faster, roughly, than like a tree-based implementation. Other thing we looked at is hash tree root. So getting the root of the tree, and we looked at this, looked at getting a root of a 10,000 large validator set, and we found that, like you'd expect, the tree implementation is significantly faster. The reason being, a lot of times you've cached intermediate nodes, and you'd have to do like significantly less hashing if you're doing repeated hashing. And so we do a lot of iteration, and we do a lot of hash tree rooting in Eth2, getting the root of the tree in Eth2. And kind of, you think about like one really high level thing that we're doing is the state transition. So we ran some benchmarks against the state transition, and just representing our beacon state as a tree or as a structural piece of data or as a byte array. And we found that the tree backing is roughly 10 to 100 times faster. So it turns out that our bottleneck was actually getting the root of the tree, and more so than like iterating over a large validator set. And that's it. Any questions? Yes.
Thank you. Thank you. That was great, very informative. But one question which I may have misunderstood, when you said 2,000 times faster, was it 2,000 times faster than previous solution, or between the state tree and serialized, or like then what?
Oh, sorry. It's the structural is, or sorry, tree backing is 2,000 times faster than a structural implementation.
Did you ever compare the byte array, like serialized form, with this one?
No. So sorry, these are just comparing the tree versus structural.
All right.
I think for a hash tree root, you'd expect the tree would still be roughly that fast. For iteration, it would probably be a little closer between structural and serialized.
And did you, sorry for the last question, if I can, did you try the actual serialized form, like some kind of byte arrayness and so on? Did you test it?
Not with the state transition, but just for iteration and hash tree root, yes. But I think we've been mainly just like focused on structural and hash tree root.
Great, thank you. Thank you so much.
Yeah, thank you. We'll go through the last talks, maybe.